Welcome. Today we're diving into the world of instruction formats, a fundamental concept in computer architecture. Instruction formats define how instructions are represented within a computer system, specifying the layout of bits for each operation. Understanding these formats is crucial because they directly impact the efficiency, flexibility, and complexity of a processor's design. In this video, we'll explore the different types of instruction formats, their structures, and the reasons behind their design choices. By the end, you'll have a clear grasp of how instructions are structured and why these formats matter in real-world computing. Let's start by defining what an instruction format actually is. In simple terms, an instruction format is the layout or structure of bits within a machine instruction. This structure determines how the CPU interprets the instruction, what operation to perform, and which operands to use. The format typically includes fields such as the operation code, opcode, source and destination addresses, and sometimes additional information like immediate values or addressing modes. The design of instruction formats is a balancing act between simplicity, speed, and flexibility, which is why different architectures may use different formats. Instruction formats are made up of several key components. The most common fields include the opcode, which tells the processor what operation to perform, and operand fields, which specify the data or addresses involved in the operation. Other possible fields are addressing mode bits, which indicate how to interpret the operands, and sometimes extra bits for flags or condition codes. The arrangement and size of these fields can vary widely depending on the architecture, but their purpose remains the same: to provide all the information the CPU needs to execute an instruction. You might wonder why there are different instruction formats instead of a single universal one. The answer lies in the trade-offs between hardware complexity, instruction flexibility, and memory efficiency. Some instructions require more operands or larger addresses, while others are simple and compact. By using multiple formats, computer architects can optimize for both performance and resource usage, tailoring the instruction set to the needs of the application and the capabilities of the hardware. Let's take a quick look at the most common instruction formats you'll encounter: 0 address, 1 address, 2 address, and 3 address formats. Each of these formats is designed to suit different types of operations and hardware architectures. We'll explore each one in detail, discussing their structure, advantages, and typical use cases. This overview will help you understand why certain formats are chosen for specific tasks. The zero-address instruction format is commonly used in stack-based architectures. In this format, instructions do not explicitly specify any operands. Instead, all operations are performed using the top elements of the stack. For example, an ADD instruction would pop the top two values from the stack, add them, and push the result back. This format leads to very compact instructions, as there's no need to encode operand addresses. However, it relies heavily on the stack for all data manipulation. To illustrate, consider a stack-based calculation like adding two numbers. The instructions might look like push 5, push 3, ADD. Here, push places values onto the stack, and ADD pops the top two values, adds them, and pushes the result. Notice how the ADD instruction doesn't specify any operands. The stack handles all the data. This simplicity makes zero-address formats ideal for certain applications, especially those with frequent arithmetic operations. The one-address instruction format is often used in accumulator-based architectures. Here, each instruction specifies a single memory address, with the accumulator register serving as an implicit operand. For example, an instruction like ADDX would add the value at memory location X to the accumulator. This format strikes a balance between simplicity and flexibility, reducing instruction size while still allowing access to memory. Let's see how a one-address instruction works in practice. Suppose we want to add the value at memory location X to the accumulator. The instruction would be ADDX. The CPU fetches the value from X, adds it to the accumulator, and stores the result back in the accumulator. This approach keeps instructions short and efficient, especially for operations that frequently use the accumulator. The two-address instruction format is a step up in flexibility. Each instruction specifies two addresses, typically one for the source and one for the destination. For example, an instruction like ADDA, B would add the value at B to the value at A, storing the result back in A. This format allows for more complex operations without requiring as many instructions, but the instruction size is slightly larger to accommodate both addresses. Consider the instruction ADDA B. Here, the CPU fetches the value at address B, adds it to the value at address A, and stores the result back in A. This format is common in many traditional computer architectures, as it allows for efficient data manipulation with fewer instructions compared to one-address formats. The three-address instruction format is the most flexible of the common types. Each instruction specifies 3 addresses, 2 sources and 1 destination. For example, add A, B, C would add the values at B and C, storing the result in A. This format is powerful for complex computations, as it allows for direct specification of all operands and the result location. However, the instruction size is larger to accommodate all 3 addresses. Let's look at an example. Add A, B, C. The CPU fetches the values at B and C, adds them, and stores the result in A. This format is especially useful in high-performance computing and scientific applications, where complex calculations are common and minimizing the number of instructions is important. Instruction formats can use either register or memory addressing for operands. Register addressing means the operands are stored in CPU registers, leading to faster execution. Memory addressing, on the other hand, accesses data directly from memory, which is slower but allows for more data to be used. The choice between these methods affects both the speed and complexity of instruction execution. Some instruction formats include immediate addressing, where a constant value is embedded directly within the instruction. This allows for quick operations without needing to fetch data from memory or registers. Immediate values are especially useful for initializing variables or performing quick calculations, but the size of the immediate field is limited by the instruction length. Instruction formats can have either fixed or variable lengths. Fixed-length instructions are easier for the CPU to decode and execute, leading to simpler hardware and faster performance. Variable-length instructions, on the other hand, allow for more compact code and greater flexibility, but they require more complex decoding logic. The choice depends on the architecture's goals and the types of applications it targets. Instruction formats differ significantly between RISC, Reduced Instruction Set Computer, and CISC, Complex Instruction Set Computer architectures. RISC architectures typically use simple fixed-length instruction formats with a small set of operations, making them easy to decode and execute quickly. CISC architectures, in contrast, use more complex and variable-length formats, supporting a wider range of operations in a single instruction. Each approach has its own advantages and trade-offs. Let's break down a typical instruction format. Most instructions include an opcode field, one or more operand fields, and sometimes fields for addressing modes or immediate values. For example, a 32-bit instruction might allocate 8 bits for the opcode, 12 bits for the first operand, and 12 bits for the second operand. The exact breakdown depends on the architecture and the needs of the instruction set. The opcode field is the heart of every instruction. It tells the CPU what operation to perform, such as addition, subtraction, or data movement. The size of the opcode field determines how many unique operations the instruction set can support. A larger opcode field allows for more instructions, but reduces the space available for other fields. Operand fields specify the data or addresses involved in the operation. Depending on the instruction format, there may be 1, 2, or 3 operand fields. These fields can point to registers, memory locations, or immediate values. The flexibility of operand fields is a key factor in the power and versatility of an instruction set. Some instruction formats include an addressing mode field which tells the CPU how to interpret the operand fields. Addressing modes can include direct, indirect, immediate, register, and more. This field adds flexibility, allowing a single instruction to work with different types of data sources. The immediate field is used to embed constant values directly within the instruction. This allows for quick operations without additional memory access. Immediate fields are especially useful for initializing variables or performing calculations with known constants. However, the size of the immediate field is limited by the overall instruction length. Some instruction formats include fields for flags or condition codes. These bits are used to indicate the outcome of operations, such as 0, carry, or overflow. The CPU can use these flags to make decisions, like branching to a different instruction if a certain condition is met. Including these fields adds power to the instruction set, enabling more complex control flow. Let's look at a real-world example, the MIPS instruction format. MIPS uses 3 main formats: R-type, I-type, and J-type. R-type is used for register operations, I-type for immediate and memory operations, and J-type for jumps. Each format has its own field breakdown optimized for its specific purpose. This variety allows MIPS to balance performance and flexibility. The R-type format in MIPS is used for register-to-register operations. It includes fields for the opcode, source registers, destination register, shift amount, and function code. This structure allows for a wide range of arithmetic and logical operations using only registers, making execution fast and efficient. The I-type format is used for instructions involving immediate values or memory access. It includes fields for the opcode, source register, target register, and a 16-bit immediate value or address offset. This format is versatile, supporting a wide range of operations from arithmetic to data transfer. The J-type format is designed for jump instructions. It consists of a 6-bit opcode and a 26-bit address field. This simple structure allows for efficient implementation of jump operations, enabling the CPU to quickly change the flow of execution. The x86 architecture uses a highly variable instruction format, with instructions ranging from 1 to 15 bytes in length. Fields can include prefixes, opcode, addressing mode, registers, displacement, and immediate values. This complexity allows x86 to support a vast array of operations, but also makes decoding more challenging. ARM processors use a fixed 32-bit instruction format for most instructions, with fields for the opcode, registers, and immediate values. This consistency simplifies decoding and execution, contributing to ARM's reputation for efficiency and performance in mobile and embedded systems. Designing instruction formats involves balancing several trade-offs: instruction length, decoding complexity, flexibility, and execution speed. Shorter instructions save memory but may require more instructions to perform complex tasks. More flexible formats allow for powerful operations but increase hardware complexity. Architects must weigh these factors to meet the needs of their target applications. Instruction formats also influence compiler design. Compilers must generate machine code that fits the available formats, optimizing for performance and code size. Complex instruction formats can make compiler development more challenging, while simpler formats may limit optimization opportunities. The interaction between instruction formats and compilers is a key aspect of system performance. The instruction format is a core part of the instruction set architecture, ISA. The ISA defines the set of instructions a processor can execute, and the format determines how those instructions are encoded. A well-designed format can make the ISA more powerful and easier to implement, while a poor design can limit performance and flexibility. Encoding is the process of converting high-level instructions into the binary format required by the CPU. Decoding is the reverse, where the CPU interprets the binary instruction and determines what action to take. The complexity of encoding and decoding depends on the instruction format. Simpler formats make these processes faster and more reliable. Each instruction may be broken down into smaller steps called micro-operations. The instruction format determines how easily these micro-operations can be extracted and executed. Clear, consistent formats help streamline this process, improving overall CPU efficiency. Instruction pipelining is a technique used to improve CPU performance by overlapping the execution of multiple instructions. The instruction format plays a crucial role here. Consistent, fixed-length formats make pipelining easier to implement, while variable-length formats can introduce complications and slowdowns. Instruction formats can also impact system security. Well-defined formats help prevent errors and vulnerabilities, while ambiguous or overly complex formats can introduce opportunities for exploits. Security-conscious architectures often favor simple, consistent instruction formats to minimize risk. Embedded systems often use streamlined instruction formats to save space and reduce power consumption. Fixed-length, simple formats are common, as they make decoding easier and hardware cheaper. These constraints drive the design of instruction sets for devices like microcontrollers and IoT gadgets. High-performance computing systems may use more complex instruction formats to support advanced operations and large data sets. These formats often include multiple operand fields and support for vector or parallel processing. The goal is to maximize computational throughput, even if it means more complex hardware. Maintaining backward compatibility is a challenge in instruction format design. Newer processors often need to support older instruction formats to run legacy software. This can complicate the design, requiring additional logic to handle multiple formats and ensure smooth operation across generations. As technology evolves, instruction formats continue to adapt. Trends include support for new data types, integration of security features, and optimization for parallel processing. Future instruction formats may become even more specialized, targeting specific application domains for maximum efficiency. To sum up, instruction formats are a foundational aspect of computer architecture. They define how instructions are represented, how operands are specified, and how efficiently the CPU can execute operations. The choice of format affects everything from performance and power consumption to security and compatibility. Understanding these formats is key to appreciating how computers work at the most fundamental level. Instruction formats aren't just theoretical, they have real-world implications. Whether you're designing a new processor, writing a compiler, or optimizing software for performance, understanding instruction formats helps you make better decisions. They influence everything from how fast your code runs to how much power your device consumes. Instruction formats are a staple topic in computer science and engineering education. Learning about them provides a solid foundation for understanding more advanced topics like pipelining, parallelism, and system security. Mastery of instruction formats is essential for anyone pursuing a career in hardware or low-level software development. Here are the key takeaways. Instruction formats define how instructions are structured and executed. Different formats 0, 1, 2, and 3 address offer varying levels of flexibility and efficiency. The choice of format impacts hardware design, software development, and overall system performance. A deep understanding of instruction formats is invaluable for anyone working with computers at a low level. Thanks for joining us on this detailed exploration of instruction formats. We've covered the basics, examined real-world examples, and discussed the impact of format choices on system design. Whether you're a student, engineer, or enthusiast, understanding instruction formats will deepen your appreciation for the inner workings of computers. Stay curious and keep exploring the fascinating world of computer architecture.